Good afternoon, everybody. This is a little different from what I normally do. Normally I buy pizza, but I think that might be a little difficult to deliver this morning. So what we're going to do is we're going to talk about pressure measurements and the things that affect those measurements and that affect your data. So basically we're going to talk a little bit about the barometric effects of water level, or on water level, the meaning of accuracy, precision, and resolution, and what those mean to you in terms of selection, barometric efficiency. We'll speak a little bit about unconfined and confined aquifer, and then we'll finish up talking about how all of those things actually affect the selection of the proper sensor for your application. Barometric effects. Barometric pressure will affect water level. Basically what we're talking about when we're looking at sensors is we're measuring pressure. And we're measuring either the pressure that water exerts, or the pressure that air exerts, or the pressure that both exert. And so in order to really look at water level data, it's necessary to be able to understand that barometric component and how it affects those measurements and how to properly compensate. Various things do affect the water level data. Obviously the accuracy and precision of the unit will. The technology of the unit itself will, whether it's a vented or a non-vented unit. And we'll discuss that here in a little bit. Barometric data collection and the compensation of that data does have an effect. Whether the hydrogeology is a confined or an unconfined unit. And last but not least, temperature equilibration. And let me speak very quickly about that. All of these units basically have a pressure sensor and a temperature sensor on them. And as you know, temperature and pressure are directly related. And so it's necessary that temperature reach equilibrium before you actually start taking your measurements. And so what I would suggest to you is that when you do put a sensor, whether it's of my manufacturer or anybody else's in the well, give it 10 to 15 minutes before you really start to try to read that data, because at first it'll be kind of choppy. And so what you want to do is you want to make sure that that instrument has equilibrated in temperature to the temperature in that water well, plus which that if it's on a cable, that cable has stretched out and relaxed and reached its full length. Otherwise, you'll start to see some slippage in early data. Some of the things that are necessary to understand really are terminology, because some of these things get thrown around a little bit, and they're not interchangeable. The three that I'd like to discuss here briefly are accuracy, precision, and resolution. Accuracy is what is my measurement to the true phenomenon. And it's really a function of hardware design and calibration techniques. And every manufacturer does not do things the same way. The USGS, for instance, when they calibrate an instrument, they calibrate it across the entire temperature and pressure range. And I think this is necessary to understand, because if you're calibrating to 3 points, as opposed to 20 points, obviously your calibration when you're doing it to 20 points is going to be a lot tighter and a lot closer. So you know, when you are selecting an instrument, I think it's necessary to make sure you understand how they've calibrated that instrument. Otherwise, you really don't know the accuracy of the data. Precision is kind of illustrated here on this little slide. Basically, precision is if I take 10 measurements, how close is each one to the preceding one? They should really kind of look like a stack of dimes. So here you see really 3 examples where you have good precision but no accuracy, or no precision, or precision and accuracy. Obviously, you want the one in the middle. The third term that is used a lot is resolution. And resolution really is, what is the smallest change I can see? Accuracy and resolution are oftentimes switched around. If somebody says I can make a measurement to 1/100th of a foot, they're not necessarily talking about accuracy. Quite often they're talking about resolution. Resolution really is the result of what is called an A to D converter. The way a pressure transducer works is a voltage is applied across and then a current is measured. And that current then is usually a 4 to 20 milliamp. That particular current is then kind of pushed through what's called an A to D, or an analog to digital converter, and change into a number that we can actually use. The smallest resolution is determined by how many bits of resolution are in that A to D converter. If it's a 16-bit as opposed to a 32-bit, well, the 32-bit can see a change that's twice as small. But just because you can see a change doesn't mean that it's accurate. So here's a good illustration of really accuracy and resolution. If I've got a ruler that's supposed to be 12 inches long, but it's 11.9 inches long, the inaccuracy of my measurement is going to be 0.1 inch. Whereas the resolution would be the little tick marks on that ruler. And if they're down to a 1/16 of an inch, well, that's the smallest measurement I can see, the smallest change I can see. So kind of when you're looking at trying to determine what is the accuracy you want, basically you take the scale of the instrument and you multiply it times the specification accuracy. In this particular case, you're looking at a 15 psi with an accuracy of 0.1%. So the smallest, or the most accurate that measurement's going to be is about 3/100ths of a foot. There are two different kinds of pressure measurements that we do, a PSIA and a PSIG. And normally at this point I say, okay, who knows what? And people put their hands up. And usually about half of the people in the room put their hands up. The other half don't. And that's understandable because a lot of people don't really understand the difference. A PSIA, or pounds per square inch absolute measurement, is a non-vented measurement that measures all pressure, all air and all water. A PSIG, however, is pounds per square inch absolute, also known as vented, measures only water level. And the reason that it measures only water level is because air is applied to the back side of the strain gauge in the same relationship that is applied to the front side of the strain gauge. So if you look at that middle slide, basically the way that it works is there's a vent tube that's attached to that back side of that strain gauge. And that vent tube runs all the way up through the cabling and is in communication to the atmosphere. And so that atmospheric pressure is being applied to the backside in the same relationship to the front side. So all you're really looking at is water level. Whereas with a non-vented sensor, the backside of that is referenced to a vacuum. And so it's measuring water and air pressure on the front side of the strain gauge. So in order to see what my true water level is, I need to get rid of that barometric pressure component. And that's done in a couple of different ways. Generally, the easiest way is you have a separate device that is going to record barometric pressure, in our case a barotrol, and it's taking barometric pressure readings at the same time that the other sensor is taking the pressure reading. And then there's a piece of software that you use that just puts the two data together and gets rid of that barometric pressure component. Another way of doing it, of course, you can do it manually. Quite often people take a manual measurement, or in some cases call the airport and find out what the barometric pressure is, and then do it in a spreadsheet. Obviously that's a lot more time consuming and not quite as accurate, but you can get, it depends on the amount of accuracy that you need in your particular application. Here's a good example of what can happen if you don't do barometric pressure compensation. This is actually a well here in Fort Collins, and it's in a confined aquifer. And so the purple line that you see there is the PSIA sensor, and the yellow line is barometric pressure. And you can see that the two move exactly together. The water pressure that is being exerted is actually the difference between the two lines. If you look down there on the 0 line, you'll see another virtually no change. Well, that's a PSIG sensor. So what we're seeing here is a case where a front has moved in and has radically changed the pressure. Matter of fact, if we didn't compensate for it, we could be off by almost 0.8 of a foot in this particular instance, where in reality virtually nothing is really happening to that water level. It's simply a change in the air pressure. Another thing one of the things that really affects water level measurements is barometric efficiency. And for the easiest way to explain barometric efficiency is just the ability of the aquifer or the vadose zone to transmit air pressure into the aquifer itself. You see here, the equation that is necessary to adjust for your barometric pressure. But basically, the easiest way to explain it is the more open the aquifer, the more unconfined, the greater the barometric efficiency. In general, barometric efficiency and water level change is greater and more pronounced in a confined aquifer. The more confined, the greater the effect. Here's kind of a nice little way of looking at it. Here you see a normal air pressure, and then a front moves in, and because the front itself is exerting less air pressure, the water level in that well actually rises because I'm not having as much water pressure pushing down on it. When the storm is over, it comes back, and the high pressure now pushes that water level back. So it can be very dramatic, as you saw in that earlier slide. Where in an unconfined aquifer, the response is in the well itself is much less pronounced because the surrounding aquifer is affected in the same relationship as the well is. Kind of a way I like to look at it is if I put a straw in a glass of water and I blow on that straw, it's going to be instantaneous in terms of the effect around it. If I take the straw and I just kind of blow on the glass of water, virtually nothing happens. So that's kind of a nice way of looking at it. So it all depends on the surrounding vadose zone and how permeable that particular vadose zone is. Here you see another illustration of an unconfined aquifer. And as you can see in this particular case, because the barometric efficiency around the well is very good, the effect in the well itself, as in relationship to the aquifer around it, is virtually nothing. So when we're looking at at selecting the sensor, there really are, I like to kind of look at it in a three-step process: accuracy, application, and budget. Well, let's look at application first. There are times when you simply can't use a gauge sensor. If you're in a situation where you're in a floodplain or where there's a high probability of flooding, you really don't want to use a gauge sensor, because if the end of that sensor, the up end of the sensor cable is submerged, two bad things are going to happen. The first thing is you're going to get water into that vent tube, and as soon as you get water into the vent tube, the mechanical equilibration of barometric pressure is compromised. The second thing is, given enough time, that water is going to work its way down that cable and into the sensor itself, and at that point, of course, it's going to short out the sensor, and you're going to have an expensive doorstop. An absolute sensor, on the other hand, really can be used anywhere. It's really good if you're in a situation where the site is prone to flooding, or if you're in a sealed well doing things like soil vapor extraction or flowing artesian. It also can have a budget consideration when a low-cost solution is required. Quite often there are absolute sensor solutions that are less expensive, and so those might be considered. Also, the sensor, when you're looking at sensor, generally speaking, an absolute sensor and a gauge sensor, the sensor price is the same, but the cable can be considerably different. I've got one application, it's a mining application down in Arizona, where there are 30 wells, and we went on site and we were looking at these wells because they were looking at instrumenting everything, and I said, well, how deep are the wells? And the guy said, well, we have shallow wells and we have deep wells. And I said, well, what's a deep well? And he said, well, they can be up to 6,000 feet deep. And I said, well, how about the shallow? And well, in this particular case, they considered a shallow well to be about 1,500 feet. Well, cable is a big cost, and a vented cable is more expensive. Matter of fact, it's probably about 50 cents a foot more expensive. So you can do a quick calculation, and in this particular case, if we used a gauge sensor with vented cable, it was going to take the project cost up about $21,000. And so, since their accuracy requirements were not quite really weren't quite that stringent, we could do an absolute sensor and do the site considerably less expensive. Another thing to bear in mind, though, is that when you're doing an absolute sensor, if you're looking for real-time data, you're not going to be able to really do real-time data because it does require a barometric pressure correction. So you've got a bit of a lag there. Gauge sensors are usually used when maximum accuracy is required, and I'm going to talk about that here in just a little bit, because a gauge sensor is, generally speaking, always more accurate than an absolute sensor. Where the site is not prone to flooding, it's a good thing to use, and when you really need that real-time compensated data. Let's go back to accuracy for a minute and talk a little bit about it. I just made a statement, which was that a vented sensor or a PSIG sensor is almost more accurate than a PSI in every circumstance. And that's really simply a matter of mathematics. Accuracy is a function of range. As you're probably aware, you get sensors anywhere from 5 PSI to 1,000 PSI. If you looked at the spec is always going to say plus or minus 0.1% full scale. But of course, if you do the math and you multiply do the multiplication of 15 PSI is going to be 0.034 feet of head accuracy, whereas a 5 PSI is going to be better than 1/100th of a foot. So it's simply a matter of the mathematics. So if you're trying to get to measurements that are 1/100th of a foot or better, there really aren't PSIA instruments on the marketplace today that will get you to that accuracy. Here's an illustration that I like to use that really brings the whole thing together. On the left you see a PSIG sensor, okay, and it's got actually a 0.1% full scale. So you're looking at basically a maximum error of plus or minus 0.42 inch. If you're looking at the identical range on an absolute sensor, you have to realize that an absolute sensor has to also accommodate barometric pressure change. And so while it may have a range that covers that 15 PSI, there's actually another 15 PSI of range on the sensor itself, because it has to accommodate that barometric pressure. So while they're identical in terms of the range, in terms of the usable range, the actual functional range on a PSIA sensor is twice as great. That means the inaccuracy is twice as great. Additionally, of course, you then have to barometrically compensated, and that particular sensor is going to have its own inaccuracy. So as you can see on this particular instance, you can be anywhere from 2 to 4 times as inaccurate with an absolute sensor as a gauge sensor. This doesn't make any difference. If I've got a lot of head and I'm trying to control a pump or something of that nature, I probably don't need those really, really tight accuracies. But if I'm doing aquifer characterization for an ISR project for uranium, I very well might need it to satisfy my permit. So really the situation is, you have to determine what your accuracy requirements are, but then use this particular data to determine the sensor that you really want to use. Last but not least is budget. Okay. Eventually money always calls the tune. And so there are times when compromises must be made to stay within that budget. And we talked about one of those earlier on the project down in Arizona, where maybe we wanted to use a gauge sensor, but money said, I really don't want to spend all that money on cable. And so as a result, that compromise was made. A couple of other things to bear in mind here. When you're you have 2 different types of cable that you can select from. You have a polyurethane cable and a Teflon, or a generic Teflon Tefcell. The reason we have 2 different kinds of cable is polyurethane is very good, very stable. Is the one that most people use. It's that black cable. If you've used our stuff, very strong. It's really good, but it has 2 characteristics that sometimes you can't use it. It is, if you are working where there's a lot of solvents present, the solvents will dissolve the cable jacketing. And so as a result, that wouldn't be if I were working on an Air Force base where they've been cleaning a lot of engines with methyl ethyl bad stuff, and it gotten into the groundwater, and if it's at high enough concentrations, it simply would not be a good situation for polyurethane. Additionally, polyurethane is semi-absorbent, and so if you're working in a contaminated situation where you're moving equipment from well to well, you have the possibility of cross-contamination, and so obviously that's would not be a good choice. And so that's where the TEF cell will come into play, because that particular cable is resistant to virtually everything in the groundwater, plus which can be totally 100% deconned. If you are using a vented system, there is some maintenance that you have to do that you don't have to do with an absolute system. And basically that is that you have to keep that vent tube clear and unobstructed. And the way that you do this is by using a desiccant. If you're familiar with desiccant, basically there's a little chamber and it just attaches to the top of the cable. I don't have a picture of it here, but I'm sure you can envision it. And inside that chamber is a desiccant, and it starts out as a kind of a blue, and will eventually go to a pink and ultimately to white. When it gets to white, it's of absolutely no value. So normally, you will change the desiccant out depending on the size and depending on where you are. If you're in Wyoming, it's going to be a little different than if you're in Louisiana. But in any case, normally those desiccant chambers are good from anywhere to 3 to 6 months. So you do need to incorporate that into your thinking and into your project costs. But if you don't use desiccant, you will end up compromising the piece of equipment. So always use desiccant and keep it fresh. You should even be using, you should use a desiccant or a cap on the cables and on the instrument itself when they're in storage, because even the atmosphere, in the standard atmosphere, you can't eventually pick up enough moisture to compromise the instrument. A non-vented or absolute instrument, since it is not open to the atmosphere, you don't need to use desiccant, so you don't have to worry about it. You can cap them up without any problem. A non-vented unit can either be on a vented cable, a non-vented cable, or no cable at all, using one of these back shells just hanging on a wire. Conversely, a vented system has to have a vented cable. It has to be open to the atmosphere. If you cap it up, what will happen is you will trap air inside of the instrument, and then as temperature changes, that air is going to expand and contract. It'll push on the backside of the strain gauge, and you will end up with faulty data. So that basically, I think I went a little fast there, but no, not too bad. So that kind of ends my portion of the presentation. Ashley Steinbeck is now going to take over, and I'm going to hand her my headset, and here you go.
So In-Situ does offer some instruments that are really tailored for your individual site needs. We do offer both absolute and vented solutions. So you really have the flexibility to choose the right equipment for your particular application, giving you, the ability to adjust for any budget concerns that you have or the required accuracy that you need. So all of our instruments do come with an extensive full-scale factory calibration, and this factory calibration is NIST traceable for pressure and temperature. So they'll come with a NIST traceable certificate of conformance, so you really can be confident in the accuracy of your instruments. Also, you can use that for reporting or documentation type purposes as well. We also have flexible communication, so the instruments come standard with built-in Modbus or RS-485, SDI-12, and 4 to 20 milliamp. So you can easily integrate these into telemetry or SCADA systems. So it really gives you some additional flexibility depending on if you need real-time data or what really your site needs. All of the instruments also work with our In-Situ 5 platform, so pretty easy to use software that really helps to simplify the data collection and data management portion. So we also have a rental department, so we can rent our water level equipment. We have a virtual hermit aquifer test kit that really allows you to characterize an aquifer by monitoring and viewing data from all the different wells that you have at the same time. So it will actually network your instruments into one central location and allows you to collect the data and analyze it simultaneously. So it really reduces your total field time. It also displays the data in a graphical form so you can actually watch what's happening in real time. We also have water level loggers for groundwater and surface water applications. So we have an absolute Rugged 100 And then we also have the gauge level troll 500 and 700 for rental purposes as well. And you can use these with the rugged cable systems and rugged readers, so you can actually communicate and do setup on your instruments right there on the site. Our rental department does give flexibility to the equipment, so you can use it both for short-term or long-term projects. So we have rental agreements that are more suited to your project. All the equipment, like our sales equipment, is factory calibrated with those NIST traceable certificates, and it also is factory maintained. So if you do rent, it actually removes you don't have to maintain the equipment to the level that we will. So you know every time you get the equipment, it's how it should be and it performs as it should. We also do have equipment consultations and product training and 24-hour technical support as well. So at this time, we would like to open it up for any questions, and we do have a few coming in. So I'll pass this back to Jim.
Okay. The first question that is posed is it necessary to use a gauge transducer to calculate barometric efficiency in a confined aquifer? And the answer there is no, it is not necessary, but it is advisable. Bear in mind what I said about an absolute sensor. An absolute sensor can virtually be used for all pressure measurements. However, you always have to subtract that barometric component before you start looking at the data. So a gauge basically has already processed that because it's already canceled it out. Number two, you mentioned variable barometric influence on confined versus unconfined units. I'm reading this, so don't mind me. How does this change in bedrock versus alluvial aquifers? Okay. Just bear in mind that the barometric influence is going to be greater the more confined the aquifer. The less confined the aquifer, the more diffuse the influence, and hence the actual effect itself. So hopefully that answers that. I think that does. Is it necessary to determine, number three, is it necessary to determine the aquifer barometric efficiency before correcting gauged water level data? No, it is the water level. If you're trying to calculate barometric efficiency, then you need to have a barometric sensor. But the data, the barometric influence has already been subtracted anytime you're using a gauge sensor.
Let them know we have a tech note.
If you have...
We also have a tech note on barometric efficiency out on our website. So if you can't find it, just let Amy know and she'll put you in the right direction.
Okay, we have another question coming in. Oh, the question is, this is on another product, it's called Virtual Hermit. Is Virtual Hermit wired or wireless? The answer is yes. Let me very quickly explain Virtual Hermit. And I'm going to do that by doing a quick history lesson. In the good old bad old days when this company first started, and I was there, basically if you were doing an aquifer test, we had a product called the Hermit. And it was a data logger that all of the data came back to one spot. The problem was you had wires everywhere because the analog pressure transducers had to be attached to the Hermit since the Hermit did the data logging and provided the power. What Virtual Hermit is basically it's a piece of hardware called a junction box that has no power, no memory in it. It simply allows the operator to talk to multiple units all at the same time. You can talk up to 15 level trolls at the same time. But the value of it is that once you've programmed everything, you can then detach as many of the of the level controls as you want and place them individually in the wells without all the wires running back and forth. So under a normal setup, what you would see is you would have the junction box and the pump well hooked so that you can see what you're drawing on, and maybe one or two of the close observation wells so you can see what was happening. But for those far out wells, you can disconnect them. But the beauty is that when you then download those, it puts everything back together as though nothing was ever disconnected in the first place. Okay, hopefully that kind of handles it. If you want more information on that, feel free to feel free to call me. My phone number is 307-760-4321. Again, 307-760-4321. I've got another question here. The question basically is what's the recommended distance for a barometric pressure sensor? How much can it cover? And that really answered in two ways. If the elevation changes are relatively the same, normally, you know, you can one for anywhere from 5 to 10 square miles is normally sufficient. However, if you have big elevation changes, and I think I saw a question earlier on where it was like an elevation change of 1,500 feet. Well, that's pretty substantial. And so in that particular instance, I would normally say you're going to need 2. So if it's fairly flat, 1. If it isn't, you know, you're going to have to make. And bear in mind, if you have a fast-moving front, if you're doing long-term monitoring, normally speaking, you know, you're going to be able to wash some of that stuff out of there if you've even got 1. Yes. Okay, the question, does the accuracy of a transducer improve if you're operating in the sweet spot? Basically, the way I'm taking that is all transducers will be a little more accurate in the middle of their operating range, okay? So if I've got a 30 psi, if I'm operating around the 15 psi range or around the 34.5 feet ahead, you know, I'm going to be a little more accurate. It used to be that it was considerably more dramatic back in the good old bad old days. Now that we calibrate across the entire temperature and pressure range to 20 different calibration points, while it does have a sweet spot, that sweet spot is considerably smaller. That does bring up a good point. When you're looking at what range to use for a particular situation, bear in mind that transducers have an operating range, and an operating range is what they call the full scale. So in the particular case of a 15 psi, it would be 0 to 34.5 feet ahead. What will happen if you exceed 34.5 feet ahead? As long as you don't exceed it by a factor of 2, in other words 69 feet, you're not going to hurt the unit, but you will not be able to trust that data because you're outside the calibrated range. So even though you're getting numbers, you're really not going to know if they're any good or not. If you exceed 69 foot, you will destroy the sensor. You quite literally burst it or pop it. Matter of fact, if you've ever seen a sensor that's been over range like that, it actually has a hole right in the middle of it. So you always want to work within the operating range. If it's very marginally over, or for just a short period of time over, as long as it doesn't exceed more than 3 times, you're going to be okay, but you won't be able to trust the data. Will a Hermit 3000 compensate for barometric pressure if it has, actually a Hermit 3000 has a built-in barometric pressure sensor, and so yes, it will compensate if you're using an absolute sensor. Can you use a vented sensor for long-term monitoring within a known saltwater intrusion aquifer? Yes. I'm not sure I quite understand where the difference would be there. One of the things, however, that you would take into consideration there is that your water density is going to be different because of the salt water. We do allow you to do a set point compensation, so that if you know what it is, or generally what it is, you can go ahead and do enter that into the programming. Actually, within the programming, you can enter in several different things. You can enter in the elevation, and you can even enter in what where your latitude is from the equator, because the closer you get to the equator, the higher, the greater the gravitational pull is, so it will change your pressure readings a little bit. Can depth to water influence barometric efficiency? I'm not sure I quite understand the question. Barometric efficiency is usually, it has to do with the vadose zone surrounding it. So I don't believe that the depth, you will see a bit of a time lag, but other than that, no, it should not affect barometric efficiency. Can I get reliable readings of pressure in a confined aquifer by using an absolute sensor in a sealed well at the surface? I'm not sure if we're talking about an artesian in this particular case, or if it's just a sealed well. To go back, an absolute sensor in a sealed well, normally speaking, I've isolated it from the barometric pressure, and so the absolute sensor should work just fine. Can you use a Rugged 100 absolute sensor for barometric? The answer there really is no. It's not calibrated to barometric to the barometric range. A separate barotrode, because it is calibrated, for the barometric pressure. What is the difference between a 500 and a 700? The difference between a Leveltrol 500 and 700 is software and memory. The Leveltrol 700 is really set up and designed to do aquifer tests, and so it will, in addition to linear, fast linear, and event sampling, it will do logarithmic sampling and step testing. So it is really set up, for aquifer tests. It's got a lot more memory, so it's the one that's normally recommended. The 500 is really set up more for long-term measurements. Okay, is there any way to correct for lunar effects on water level? That's a good question. I don't have that answer for you. I'm sorry. Besides moisture concerns at the surface, are there situations where you would not want to use a gauged transducer? Yes. Matter of fact, we had a discussion earlier today, and the discussion was, should you use when we were talking about a flowing artesian, okay, and where we were trying to obviously measure, the pressure inside the flowing artesian, and an absolute sensor in this particular case would be the one that I would want to use, because just bear in mind that on the front side of that strain gauge, I've got all pressure, that's inside that pipe. If I take a gauge sensor, then I'm applying some barometric pressure to the backside of that strain gauge that really should not be applied in that particular case. So there are some times when you might not want to use a gauge sensor. Okay, do you have a recommended distance for a single barrel auger? Okay. For instance, a well nests that are located across tens of miles. I think I actually answered this before. Normally speaking, again, usually 10 square miles is kind of what they're talking. But again, it kind of comes down to what your application is. If you're doing long-term monitoring, and if you're not trying to get very, very tight accuracies, you may very well be able to get away with one. I guess what I would suggest in that particular instance is I would try one. Okay, and then I would see how that did. Put it in the middle. Okay, if I've got 4 nested wells and they're 30 miles apart, take the one in the middle and then compare your data and see how you're doing. If you say no, that just isn't going to get it, then you get a second one or a third one. So I'm kind of cheap, and so I kind of put my foot in the water and kind of work my way through it. How sensitive are Rugged 100s to freezing wells? If they are only a few feet below ground, will the output data be obviously off? Freezing and pressure sensors do not go well together. Okay, what will happen is ice will form inside and press up against that sensor, and given enough time and enough energy, it will burst the sensor. So you don't want to deploy a pressure sensor in a situation where it is going to freeze. Okay. groundwater depth, you know, I mean, obviously if it's very deep, it may be not as prone to flooding. There are some ways that you can cushion the effect. I have seen where people have quite literally taken like a slimline plastic bag and put a little bit of environmentally friendly antifreeze or even alcohol in it, and you read it at the surface and you calculate your offset, and then you can put it down, and that will work. Down in a groundwater well, that'll work pretty well. If you're using it in a flowing water situation, then usually you don't have to worry about it at all, because as long as you've got some flow, you won't have to worry about ice. But that is certainly a consideration. Oh, wait, I got one more. Besides seal sortition, are there any other situations where
Gauge transducer points.
I'm thinking. The question is besides the sealed artesian, are there any situations where you would not want to use a gauge? You know, anytime you're trying to determine total pressure, then you want to use an absolute, okay? If you are, anytime where you are trying to do water level, generally speaking, as I say, other than, you know, maybe soil vapor extraction, things of that nature, where you're reading vacuum, or, you know, then you wouldn't want to use a gauge sensor in that particular instance, although we do have a technique where you actually can use a gauge sensor where it vents into the headspace itself and the vacuum is applied to the backside. But by and large, gauge sensors, when you don't want to use them, would be where you're trying to get total pressure or where you're prone to flooding. Normally, other than that, generally can be used. Does in situ software take into account barometric efficiency? The answer is no. You know, that would be a separate calculation. My colleagues just say, well, we can use baromerge, but baromerge doesn't actually do barometric, but doesn't do barometric efficiency. It just takes the barometric component out of the pressure measurement. Okay. Can a barrel? Yes. Can a barotrail be hung in freezing air temperatures below 32 F? Yes. You know, as I say, the freezing thing has to do with water and that ice pushing against the strain gauge. So I believe the storage temp on a storage spec on a barotrail is well below freezing. So so that should not cause you any problem whatsoever. Okay, that seems to be all of the questions. If you have any more, as I said, we got a lot of good tech notes on the web. I don't know who signed up. I assume a bunch of you know me. Feel free to call me if you have questions. If we don't have an answer, we've got a lot of resources. Thank you very much.